Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. Belongs to 5th semester and this is nothing but your core 11 paper. And this class is a somewhat special class. In this class we are going to be discuss determination of psi x wave function by boundary condition. That is the boundary condition is psi x tends to 0 for x tends to plus or minus infinity. This is one of the boundary condition. By using this boundary condition we can found the psi x. So this boundary condition we have been used in our potential step and finite potential well. So whatever we have been discussed in our class at that time, that things also can be represented in other way. You can found some other books, they have been represented in different way. You just watch, don't write in the note, you just watch that what I am trying to explain to you. Okay, so you can check your note that when we discussed for potential step, that is E less than V0, you just go to this page wherever you written in your note. For that we defined the time independent Schrodinger equation for region 1 and region 2. Okay, and we got the solutions for region 1 is this one and region 2 is this one. Okay, at that time we have been discussed that this is the wave function belongs to incident wave and this is the belongs to reflected wave and this is represents exponentially increasing wave function and this is exponentially decreasing wave function. So and at that time we have been discussed that if we will consider C e to the beta x as a wave function, then for x at that time what we discussed, see, for x tends to infinite, C e to the beta x tends to infinite, but according to boundary condition a acceptable wave function has to follow that x tends to infinite, the wave function should be tends to 0. That means what I told that psi x, any wave function should have to be 0 when x tends to plus or minus infinity. So but this C e to the beta x could not be follow this boundary condition, so hence C e to the beta x not to be considered. So finally we consider that our psi 2 will be this much, psi 2 x will be d e to the minus beta x and C e to the beta x not to be considered. In this way we have been represented whenever we have been discussed this portion. Okay, this portion. Okay, some other books they have been represented in this fashion. You just watch, no need to write in your note, but you can write in your rough. So in exam you can write, you can represent in either way, but either in this way or what I am going to explain. See, we found that psi 2x is equal to C e to the power beta x plus d e to the minus beta x, right? So here we explained that this will be infinite when x tends to infinite, but it has to be 0 when x tends to infinite, hence this is not to be acceptable. So some other books, how they have been written, that they directly used this boundary condition in this fashion. See, psi tends to 0 when x tends to plus or minus infinite, right? And here in the region 2, this is the region 2. So region 2, that means x is increasing up to plus infinity. So we have to consider in this way that psi 2 has to be 0 when x tends to infinite. That means I have to put C e to the power beta infinite plus d e to the power minus beta infinite. right? So will be equal to 0 is equal to here c e to the power beta into infinite. Beta multiplied with infinite means e to the power infinite plus d into e to the power minus infinite. So here e to the power minus infinite means tends to 0, we can put 0. So here what we got, that c into e to the power beta will be equal to 0, right? So this could not be 0 because e to the power infinite will be infinite. So hence c will be equal to 0. So if c we are going to be consider is going to be 0, then automatically psi 2, what we can write, psi 2x, this one will be d e to the power minus beta x. So in this fashion also some books they have been represented. Okay, so another problem we have been discussed, that is potential well. There also we are going to follow the potential well. There also we have been explained in this fashion. Okay, we explained in this fashion, but somebody can be explained or represent in this way. I am going to show you. Wait. So this is our finite square well potential. Here region 1, 2, 3, and we have been written the time independent Schrodinger equation for region 1 and 2 and 3, and corresponding wave functions are this and this, right? So psi 1 is nothing but belongs to wave function of region 1, and psi 2 region 2, psi 3 is region 3. Okay, so as we know that according to boundary condition, any wave function is tends to be 0 when x tends to be plus or minus infinity, right? First we have to consider psi 1 for here for this potential well case. Here we found psi 1 is a e to the power kx plus b e to the minus kx. Here I am going to draw that figure. It will be easy for me, that this is minus v0, this is minus a and plus a, and this towards this is extends up to minus infinity, this side is plus infinity. Region 1, region 2 and region 3, and this is our wave function belongs to region 1. Now this wave function has to be 0 when we have to move towards the minus infinity, because this is belongs to region 1. Region 1 is extends up to this side minus infinity. So we are going to do so. Here we have to apply the boundary condition, this one, that psi 1 will be 0 when x tends to minus infinity, means a e to the minus, here x instead of x I have to write minus infinity. So minus k infinite plus b e to the power k plus infinite, because if I am going to put minus infinite, it will be plus infinite. So here this will be 0 because e to the power minus infinity will be 0. So 0 equal to 0 plus b e to the power infinite. So boundary condition told that psi 1 should have to be 0 if we have to consider x is equal to minus infinity. So if it is so, then this should have to be 0, but e to the power infinite could not be 0. So b equal to 0, b will be equal to 0, hence psi 1 will be considered as a e to the power kx. Okay, but when we have discussed this topic, at that time I have been explained in this manner, that we know that for a well behaved or acceptable solution, the wave function should be obey the boundary condition as psi x tends to 0 for x tends to plus or minus infinity. So b e to the power minus kx, if we are going to consider this term for region 1, and this will be infinite for x tends to minus infinite. So as this is not obeying the boundary condition, this one, so this term is not going to be acceptable. Likewise for region 3 also, this term is not going to be acceptable if we are going to consider x tends to plus infinite. So in this fashion we have been represented at that time. I have been represented at that time, but anyone can also represent or write in this fashion in the exam. There is no issue, okay, no problem. You don't change your note, but you just remember in this fashion also we can write the psi 1, or we can finally write the psi 1 will be equal to a e to the power kx. Likewise psi 3, if we are going to consider psi 3 is our f e to the power kx plus g e to the power minus kx. Psi 3 is belongs to this side, that means it has to be extend up to plus infinite. So if this wave function has to be obey the boundary condition, it should have to be 0 when we have to consider x tends to infinite, k infinite plus g e to the power minus k infinite. So this term is going to be 0, but this term is going to be infinite. That means 0 equal to f e to the power infinite. Okay, so hence the e to the power infinite is equal to infinite. So this could not be 0. So f should have to be 0. So hence finally the psi 3 should have to be g e to the minus kx, where f e to the power kx term is not going to be considered. So in this fashion or in this manner can be represented by anybody. Okay, so here also this f e to the power kx is not going to be considered. So finally we written that psi 3 will be g e to the power kx. So in this way we have been written. Some books they have been written in this fashion, some books they have been written in this way. So anyone can be right either this way or this way, no issue. Okay, so thank you so much.